Let's talk about eigenvalues and eigenvectors. In some applications, we are interested in a vector x, such that ax equals lambda x for some scalar lambda. Lambda is a Greek letter, it's the equivalent of our L. An eigenvector of an n by n matrix A is a non-zero vector x, such that ax equals lambda x for some scalar lambda. The scalar lambda is an eigenvalue of A. We need to see an example. Let A equal 1, 6, 5, 2, x equals 6, negative 5. Is x an eigenvector of A? It's an eigenvector of A if ax equals lambda x for some scalar lambda. Let's calculate it. Here's ax. Multiply it out, you get negative 2420. Hey, notice, that is a multiple of x. It's negative 4 times our vector x. It's negative 4 times 6, negative 5. So x is an eigenvector of A, and lambda equals negative 4 is the corresponding eigenvalue. How about x equals 1, 2? Is x an eigenvector of A? Let's check it out. Ax, when you multiply it out, is 13, 9. Oh no, that doesn't work out at all. That is not a multiple of 1, 2 for any scalar. It does not equal kx for any scalar k. So x is not an eigenvector of A. Here's how to find eigenvalues and eigenvectors. We're looking for non-zero solutions x to ax equals lambda x. Let's get everything on one side. It is so tempting to factor out x and say, okay, so now we've got a minus lambda times x equals 0, but that's wrong. That makes no sense at all, because you can't have a minus lambda. A is a matrix, lambda is a scalar. It's a constant. You just can't do that. Here instead is what we can do. We're going to rewrite lambda x as lambda I times x. Here I is the identity matrix, because multiplying a vector x by a constant lambda is the same thing as multiplying the identity matrix by lambda and then taking that resulting matrix and multiplying it by the vector x. That'll give you the same result. And now we can factor out x, because both A and lambda I are n by n matrices. Okay, we know x equals 0 is the solution. There are non-zero solutions x if and only if the determinant of A minus lambda I equals 0. We've seen this before, that an equation like this has a non-trivial solution x if and only if the determinant of this thing is 0. So that's what we're going to try to do. We're going to try to solve determinant of A minus lambda I equals 0. The values of lambda for which determinant of A minus lambda I equals 0 are the eigenvalues of A. Once we know these, we can find the values of x for which A minus lambda I x is 0. Those will be the eigenvectors. So find the eigenvalues and the corresponding eigenvectors for A equals 7, 4, negative 3, negative 1. We find the eigenvalues by finding the determinant of A minus lambda I and setting it equal to 0. Okay, we know what I looks like. I is just going to be 1, 0, 0, 1. Okay, you multiply that by lambda, and then you're just going to get lambda 0, 0, lambda. So you subtract that from A, and you're basically subtracting lambdas from the diagonal. So the determinant of A minus lambda I is the determinant of 7 minus lambda, 4, negative 3, negative 1 minus lambda equals 0. We know how to calculate a determinant. Product of these minus the product of these. That's going to be negative 7 minus 6 lambda plus lambda squared plus 12 equals 0. When you multiply it out, simplify, and you get lambda squared minus 6 lambda plus 5 equals 0. So this is the determinant of A minus lambda I, which we call the characteristic polynomial for A. Eigen is German for characteristics. So we have eigenvectors, eigenvalues, but we have a characteristic polynomial. It is the polynomial determinant of A minus lambda I. So let's factor that. Set it equal to 0, we factor, we get this. So it looks like the solutions are going to be lambda equals 5 and lambda equals 1. Thus the eigenvalues are lambda equals 5 and lambda equals 1. Now let's find the corresponding eigenvectors for each eigenvalue. These are the values of x for which A minus lambda I x equals 0. Let's go ahead and find those values of x. So A minus lambda I x equals 0. First, what happens when lambda equals 5? Plug in lambda equals 5 into here, and we get this 7 minus 5, 4, negative 3, negative 1 minus 5 times x equals 0. Simplifies to this. There's the augmented matrix. Get it in reduced echelon form. That's what we have. So this is x1 plus 2x2 equals 0. In other words, x1 equals negative 2x2. So x1 is negative 2x2. x2 is simply x2. Therefore, x1, x2 is x2 times negative 2, 1. Any multiple of negative 2, 1 is a solution. So this is an eigenvector for the eigenvalue lambda equals 5. How about for the eigenvalue lambda equals 1? Again, let's solve this. Plug in lambda equals 1. This is what we'll end up with. 7 minus 1, 4, negative 3, negative 1 minus 1. That simplifies to 6, 4, negative 3, negative 2 times x times x1, x2 equals 0. Here's the augmented matrix. This is what the reduced or echelon form of that matrix looks like. So we have x1 plus 2/3 x2 equals 0. In other words, x1 equals negative 2/3 x2. So x1 is negative 2/3 x2. x2 is simply x2. Therefore, our solution is x1, x2 is x2 times negative 2/3 x1. So any multiple of negative 2/3, 1, is a solution. So this is an eigenvector for the eigenvalue lambda equals 1.